So in this meeting, I'm going to continue going over section 1.2 of the textbook, sections on problem solving with patterns. And I'm picking up today on this topic about the Fibonacci sequence. And you want to start by reading what's in the textbook, and then the comments today are going to go just a little beyond what's in the textbook. I want to show you a method for solving these difference equations that works in general or in a wide range of problems. And there's a similar method in a subject called differential equations, which is real important in physics. And I think it's just a good example of how to deductively approach finding a pattern. And so the Fibonacci numbers, you start with 0 and 1, and you add those two together, you get 1. So now your sequence goes, let me move my camera over here so I can write for you. So your sequence goes 0, 1, then you add those two and you get 1, and then you add the 1 and the 1 and you get 2, and then you add the 1 and the 2 and you get 3. The 3 and the 5 here make 8. And so it goes. So for any one of them, like let's call this the nth Fibonacci number. If n was 1, 2, 3, 4, 5, if n was 5, this would be Fn, the fifth one. And how do you get it? You take the one before and the one before that, and you add them together. So this is an example of what you call a recurrence relation. It tells you how to get one of them in terms of the ones that you've already got. And to make this particular sequence, you start with F0 equals 0 and F1 equals 1. It gives you the starting points here and here. Now, what I'm going to talk about is just the recurrence relation for the moment. I'm going to cross through this just to get, because I want you to kind of ignore the starting point. You could make a sequence like this. You could pick any two numbers to start with, and you'd create a sequence like the Fibonacci sequence, but different starting points, different numbers all the way through. Okay. Now, the question is, if we just ignore the starting point, can we come up with a formula, a way to generate a bunch of numbers that would satisfy this recurrence relation? And here's the idea. Maybe Fn could be some constant times another constant, x to the nth power. And why would we even think so? Well, because if you put that in the equation here, you see, Fn would be a times x to the n, and Fn minus 1 would be a x to the n minus 1. And fn minus 2 would be a times x to the n minus 2. So, well, a clearly doesn't matter. You could put any old constant in there you want, and because it's going to cancel out on both sides. So you divide both sides by a, and it's gone. So we could use any old number we want. And then here, this equation, try to figure out what does the x need to be, that's going to simplify real nicely. If I factor out the x to the n minus 2, I have x to the n minus 2 times 1 plus x. See, x to the n minus 2 times 1 is just x to the n minus 2. X to the n minus 2 times x is just x to the n minus 1. See, I factored out x to the n minus 2 on both sides. Divide both sides by x to the n minus 2. And it's gone. So we're down to just x squared equals 1 plus x. So subtract the x from both sides. Subtract the 1 from both sides. And you get this simple quadratic equation. So if I can just find a number that satisfies this equation, so there'll just be a couple of special numbers x that solve this. But you take one of those special numbers, use it for the x here, and then let a be anything you want. And you've got a formula that'll generate. You put in an n, it gives you the nth number in a sequence. And what's the starting value? Well, if n was 0, then a is going to be the first number in your sequence, because x to the 0 would be just 1. Okay. Now, you can't generate necessarily the Fibonacci sequence this way, but you will generate a sequence of numbers that just satisfies the recurrence relation. And in fact, we'd make two different sequences. There's going to be two different numbers that satisfy this quadratic equation, two different x's you could use in here, make two different sequences that satisfy that recurrence relation. And then we'll figure out how to get the right ones to satisfy it, to make the actual Fibonacci numbers later. Okay. So what are the solutions to this? Well, you know, you may have learned in an algebra class, ax squared plus bx plus c equals 0 has two solutions. Negative b plus or minus the square root of b squared minus 4ac over 2a. So how do I make this look like? See, this is 1 times x squared plus -1 times x plus -1 equals 0. I'm just rewriting that equation. So now you see that matches ax squared plus bx plus c equals 0. So x is -1, that's 1, plus or minus the square root b squared, that's -1 squared, -1 times itself, that's 1, minus 4 times 1 times -1. All over 2 times a, that's just 2 times 1. That's 2. Okay. So I get 1 plus or minus the square root of 5 over 2. There's two different solutions. Either x is 1 plus the square root of 5 over 2, which is the golden ratio, sometimes use the letter phi for that, and then or x is 1 minus the square root of 5 over 2. And there's a letter sometimes used for that is psi. So x could be either phi or psi. Okay. Now, so how do I make my sequence? See, if I make the sequence of those numbers with different n's, that would satisfy the recurrence relation, regardless what a might be. But also, take any old b that I want, those ones satisfy the recurrence relation. And even if I add them together, if I do any combination like that, it's gonna be okay. It's still gonna do see, these will add up to that. And then this one, this is supposed to be a psi. Psi to the n minus 1 plus b, psi to the n minus 2. Those are going to add up to this. So that's still regrouping, putting these together. That plus this See, the nth one is still, let's call this Fn. It's still Fn minus 1 plus Fn minus 2. So I've got, no matter what A I pick or what B I pick, if this is how I make my nth number, then I'm making my nth number in a way that satisfies the Fibonacci recurrence relation. So, depending on how I pick the A and the B, I could make many different Fibonacci type sequences. But if I want A1 to equal 1, or F1 to equal 1, and I want F2 to equal 1, what does that mean? It means A phi plus B psi equals 1. And a 1 there. And it also means, oh, well, let me do the 0 and the 1. So A phi to the 0 plus B psi to the 0 should equal 0. And A phi to the 1 plus B psi to the 1 equals 1. Now anything to the 0th power is just 1. So we have A plus B equals 0. So A is minus B. So B is minus A. And then the second equation, I have A times phi plus, but B is just negative A. So I'll have negative A psi equals 1. So A plus B equals 0, or B is negative A. And then A phi minus A psi equals 1. Okay. So B is the opposite of A. And A times phi minus psi equals 1. So B is the opposite of A, and A is 1 over phi minus psi. Now, we've already worked out phi and psi on the previous page. You know, when you simplify this thing, putting in those numbers, you get 1 over the square root of 5. Okay. So if you want to generate numbers that satisfy the recurrence relation, do anything in this form. And then if you specifically want to start out with 0 and 1, you've got to choose the right A and B. And so then you come up with Fn is 1 over root 5 phi to the n minus 1 over root 5 psi to the n or just phi to the n minus psi to the n over root 5. So that gives you a closed form, a formula where you just put in the n and you get out the nth number. So this is a way of going from a recurrence relation to a closed form solution. So if you have a formula that lets you get from one moment or the previous moment to the next, then you can figure out where you are at any time. And it's a similar kind of approach that also works for equations of motion in physics, where knowing the rule for how you go from one moment to the next sometimes lets you work out a formula for where you'll be at any time. Okay, that's it for this topic.